Hello everyone. In the previous class, I was discussing about the derivation related to shape functions of beam element. They are Hermite shape functions. In addition to that, I have discussed the stiffness matrix of beam element and also the load vector due to uniformly distributed load for the beam element. So today, let us start with the numericals related to beam. So in the first numerical, there is a simply supported beam having two supports and is subjected to an UDL of intensity 12 kilonewton per meter for its entire length of 1 meter. And the Young's modulus of material of this beam is 200 GPa, and moment of inertia I is equals to 2 into 10 to the power of 6 millimeter to the power of 4. So it is asked to find the maximum deflection for the beam. So here you have to understand that for a simply supported beam subjected to UDL for its entire length, the maximum deflection will be at the center of the beam. The maximum deflection will be at the center of the beam because the concentration of UDL will be at the center. So now the given data are E is equals to 200 GPa, which I have kept in kilonewton per meter square and I in meter to the power of 4. So here in all the numericals related to beam, it is required to keep the unit of force in terms of kilonewton and unit of length in terms of meter. To handle it properly, it is required to keep the units of force in terms of kilonewton and unit of length in terms of meter. So E in terms of kilonewton per meter square is 2 into 10 power 8, and moment of inertia I is 2 into 10 power minus 6 meter to the power of 4, and the length of beam is 1 meter. Now, it is required to follow the same set of steps in order to solve the problems related to beam as followed in analysis of bar and analysis of trusses. So, the first step is having the formulation of the finite element model, or it is discretization of the given continuum. So it is a single beam element having two nodes, node 1, node 2. The value of zeta may vary from -1 to +1 for the length of 1 meter, or it is equals to L. And it is assumed that the deflection at node number 1, linear deflection at node number 1 is V1, and rotation at node number 1 is theta 1. Linear deflection at node number 2 is V2, and rotation at node number 2 is theta 2. So this is the first step in finite element method, wherein we have shown the number of nodes and element and the value of zeta at node 1 and node 2 and the corresponding degrees of freedom associated with node 1 and node 2. Now, in the second step, we have to formulate the elemental stiffness matrices. Now, as there is only one element in the given continuum, definitely there will be only one stiffness matrix, and the elemental stiffness matrix itself will be the global stiffness matrix. So, the stiffness matrix of beam element is given by this expression or this matrix. So, where K is given by EI by LE cube in the matrix of 12, 6 LE, minus 12, 6 LE, 6 LE, 4 LE square, minus 6 LE, 2 LE square, minus 12, minus 6 LE, 12, minus 6 LE, 6 LE, 2 LE square, minus 6 LE, 4 LE square. Now we know the value of E, we know the value of I, even we know the value of length of the element, which is 1 meter. So E value is 2 into 10 power 8 kilonewton per meter square. I is 2 into 10 power minus 6 meter to the power of 4, and length of element is 1 meter. So substituting these values, we ultimately get K as equals to 400 in the matrix of 12, 6, minus 12, 6, 6, 4, minus 6, 2, minus 12, minus 6, 12, minus 6, 6, 2, minus 6, 4. And these entities are these entries in the matrix are associated with the degrees of freedom corresponding to node 1 and node 2. They are V1 theta 1, V2 theta 2. In column also they are associated with V1 theta 1, V2 theta 2. Now the global displacement vector as it is consisting of two nodes with 2 degrees of freedom at each node. So globally it is consisting of V1 theta 1, V2 theta 2. And as the beam is subjected to uniformly distributed load, we know how to calculate the load vector for a UDL. So the load vector due to UDL is given by the matrix P naught LE by 2, P naught LE square by 12, P naught LE by 2 minus P naught LE square by 12. And it is they are associated with V1 theta 1, V2 theta 2. Now, P naught is the intensity of UDL, which is 12 kilonewton per meter, and LE is length of the member, which is 1 meter. Now, I have considered here minus 12 kilonewton per meter because UDL is acting in the downward direction. So, therefore, load vector due to UDL, F is equals to, it is minus 12 into 1 divided by 2, minus 12 into 1 square divided by 12, minus 12 into 1 divided by 2, minus of minus 12 into 1 square divided by 12, which is the load vector due to the UDL, which is equals to minus 6, minus 1, minus 6, 1. So this corresponds to the load vector due to a single beam element. Now, as the problem itself is consisting of only one element, one single beam element, definitely the stiffness matrix, what we have calculated here, it itself is the global stiffness matrix, and the displacement vector itself, whatever it is, V1 theta 1, V2 theta 2, it is there, it is the global displacement vector, and the value of forces, they are minus 6, minus 1, minus 6, 1 corresponding to V1 theta 1, V2 theta 2 is itself is the global force vector. Now the next step is to formulate the overall equilibrium equation, and for the overall equilibrium equation it is K into Q is equals to F. K is global stiffness matrix, Q is global displacement vector, and F is global force vector. Now the next step is to apply the boundary condition, and looking at the problem, the node 1 is completely fixed and node 2 is having the roller support. So node 1 is completely fixed, meaning that it is not having displacement along vertical direction, horizontal direction, and also the rotation at this location. Whereas the node 2 is associated with roller support and it can have the displacement along horizontal direction, but it is constrained along the vertical direction. So meaning that the value of V1 and theta 1 is equals to 0, and also the value of uh, V2 as the vertical constraint at node number 2, then definitely V2 will be equals to 0. But theta 2 is not equals to 0. So substituting the boundary condition for the overall equilibrium equation, V1 is 0, theta 1 is 0, and V2 is 0. So it is corrected. It is to be corrected here. It is not V1. It is V2 here. So it is V2. This is V2, and as V1, theta 1, V2 are equals to 0, eliminate the corresponding rows and column associated with V1, theta 1, V2. Then the remaining matrix is 400 into 4 multiplying with the theta 2 is equals to 1, or theta 2 is equals to 6.25 into 10 power minus 4 radian. So the global displacement vector, that is V1 theta 1, V2 theta 2, V1 theta 1 and V2 are equals to 0, and theta 2 is 6.25 into 10 power minus 4 radian. So to find the maximum deflection, to find the maximum deflection, we know that V is equals to H into Q, where V is the field variable, H is the safe function, matrix of safe function, and Q is the displacement vector corresponding to the beam element. And we also know that this field variable can be expressed as H1 V1 plus LE by 2 H2 theta 1 plus H3 V2 plus LE by 2 H4 theta 2. And we also know that V1 is 0, theta 1 is 0, V2 is 0. So therefore, we will be having the field variable V is just equals to LE by 2 H4 into theta 2. And H4 is equals to, we know that H4 is given by 1 by 4 minus of zeta. So minus 1 minus zeta plus zeta square plus zeta cube. And for a beam element, looking at the problem, the value of zeta is varying from minus 1 to plus 1, and zeta is 0 at the center, where there is a maximum deflection of the beam is taking place. So for this equation, it is required to substitute For this equation, it is required to substitute the value of zeta as 0, theta 2 as 6.25 into 10 power minus 4, and Le as 1 meter. So V is therefore equals to V is maximum when zeta is equals to 0, and V maximum is minus 7.8125 into 10 power minus 5 meter. So hope everyone have understood this numerical. I'll just have the overview of this numerical once again, wherein there is one single beam element which is subjected to UDL for its entire length. Node 1 is fixed completely, node 2 is having the roller support, and I have shown here the degrees of freedom in terms of V1 theta 1, V2 theta 2, and we have to formulate the elemental stiffness matrix. As there is only one element, definitely the elemental stiffness matrix itself is the global stiffness matrix, and global displacement vector is consisting of V1 theta 1, V2 theta 2, and load vector due to UDL is given by this expression or matrix. And when you substitute the intensity of UDL and length of element, we will definitely get the load vector due to UDL as minus 6, minus 1, minus 6, 1. And when you formulate the overall equilibrium equation and apply the elimination method of boundary condition, V1 theta 1, V2 are equals to 0, because node 1 is completely fixed and node 2 is having the roller support. For a roller support, vertical displacement is completely constrained. So therefore, V1 theta 1 and V2 are equals to 0. Eliminate the corresponding rows and column and simplify, we'll get the value of theta 2. It is the rotation, therefore the unit of this is in terms of radian. So to find the maximum deflection for a beam subjected to UDL, definitely the maximum deflection will be at the center, where the value of zeta is equals to 0, as zeta is varying from minus 1 to plus 1. I have just written the field variable where we are interested to find the maximum deflection is equals to Le by 2 H4 theta 2. This we got after elimination from this equation, wherein we have substituted V1 theta 1 V2 r is equals to 0, and ultimately we left out with this equation where we have to substitute zeta as 0, theta 2 as 6.25 into 10 power minus 4, and Le as 1 meter. So ultimately, we'll get the maximum deflection, which is at the center of the beam, as minus 7.8125 into 10 power minus 5 meter. So considering one more numerical, here it is consisting of two elements beam. So node 1 is completely fixed, node 2 is having the roller support, node 3 is also having the roller support, and between 2 to 3 we have a UDL of intensity 12 kilonewton per meter. E value is again 200 GP, I is 4 into 10 power 6 millimeter to the power 4. It is asked to find the rotations at node number 2 and node number 3, meaning that we have to find the value of theta 2 and theta 3, and also we have to find out the maximum deflection at the center of the beam carrying UDL. So it is a two element beam, wherein element 1 is between node 1 and 2 and element 2 is between node 2 and 3. So I have written the given data here, given data, E value, I value, L1, L2, EI we have calculated here itself because it is required in the stiffness matrix. So the first step is finite element formulation. There are two elements. Element 1 is connected between node 1 and 2. Element 2 is connected between node 2 and 3. And the degrees of freedom associated with node 1 are V1 theta 1. Degrees of freedom associated with node 2 are V2 theta 2. Degrees of freedom associated with node 3 are V3 and theta 3. So I have written here the length of first element and second element in terms of L1, L2, and L1 and L2 are equals to 1 meter. So first of all, we have to formulate the elemental stiffness matrices by using this stiffness equation. So we have the value of EI and also the length of element. So definitely when you substitute the length and EI value, we get the stiffness matrix, and element 1 is associated with node 1 and node 2, node 1 and node 2, and meaning that they are associated with the degrees of freedom V1 theta 1, V2 theta 2. So after having this stiffness matrix, on the top of it, you have to write the V1 theta 1 and V2 theta 2. In column also, it is V1 theta 1 and V2 theta 2. Similarly, when you calculate the stiffness matrix for element 2, so EI value is again 800 kilonewton per meter square, and length of the element is 1 meter. And when you substitute the value of EI and L2 in the stiffness equation or stiffness matrix of beam element, then we will get this expression. And stiffness matrix is element 2 is associated with node 2 and node 3, and the degrees of freedom corresponding to node 2 are v2 theta 2 and node 3 are v3 and theta 3. So on the top of it, it is written as v2 theta 2 v3 theta 3, and on the column also it is written as v2 theta 2 v3 theta 3. Next is to have the global stiffness matrix, that is summation of K1 plus K2. So in the both the matrices, outside the matrix it is 800, and the total degrees of freedom are 6. That is V1 theta 1, V2 theta 2, and V3 theta 3. So therefore, it is required to consider a 6 by 6 empty matrix before formulating or before having the assembly of the stiffness values. So here a 6 by 6 matrix is considered. On the top of it, it is written as V1 theta 1, V2 theta 2, V3 theta 3. In column also, it is written as V1 theta 1, V2 theta 2, V3 theta 3. Each entity is searched in K1 and K2. So V1 cross V1, it is available in K1, so which is 12. It is written here 12. Theta 1 cross V1, theta 1 cross V1 is available in again in K1, which is equals to 6. So like this, it is formed. The complete assembly is formed by searching each entity of the matrix. And globally, when you see the displacement vector, so definitely it is associated with 3 nodes, and at each node there are 2 degrees of freedom system. Totally there are 6 displacements in terms of V1 theta 1, V2 theta 2, V3 theta 3. So it is global displacement vector. And global force vector is associated with F1, F2, F3, F4, F5, F6 corresponding to each degrees of freedom of the beam. So it is associated with V1, this is F2 is associated with theta 1, and F3 is associated with V2, F4 is associated with theta 2, F5 is associated with V3, and F6 is associated with theta 3. And we know that there is a UDL between node 2 and 3. So definitely as node 1 is fixed and it is a fixed end, the force acting along V1 direction and theta 1 direction will be equals to 0. And between F3 to F6, meaning that between node 2 and 3 there is a UDL, and we know how to calculate the load vector due to UDL, and it is given by P naught LE by 2, P naught LE square by 12, P naught LE by 2 minus P naught LE square by 12. When you substitute the intensity of P naught and the length of element, we get the force vector, global force vector for the entire beam problem. So next we have to formulate the overall equilibrium equation, which is K into Q is equals to F, where K is global stiffness matrix, Q is global displacement vector, and F is global force vector. So looking at the problem, the boundary conditions are node 1 is completely fixed, meaning that the value of V1 and theta 1 is equals to 0. And node 2 and 3 are having the roller support, meaning that V2 and V3 are completely constrained or they are equals to 0. So therefore, applying the elimination method of boundary condition for this equilibrium equation, meaning that we have to apply V1 as 0, theta 1 as 0, V2 as 0, V3 as 0. Eliminate the corresponding rows and column associated with V1, theta 1, V2 and V3. So eliminating first row, first column, second row, second column, third row, third column, fifth row, fifth column. So these to be eliminated, and the remaining matrix will be 800, 8, 2, 2, 4, theta 2, theta 3 is equals to minus 1 plus 1. And in simplify this, definitely we get theta 2 and theta 3 values, and they are minus 0.2679 into 10 power minus 3 radian, and theta 3 is equals to 0.4464 into 10 power minus 3 radian. So this is the nodal displacement vector. V1 theta 1, V2 are equals to 0, theta 2 value it is written here, and V3 is 0, and theta 3 value is written here. So to find the maximum deflection for the beam carrying UDL, so the value of zeta is considered from node 2 to node 3 as minus 1 to plus 1. So the value of zeta from node 2 to node 3 is considered as minus 1 to plus 1, and the maximum deflection again it is at the center of the UDL. So therefore, when I substitute the condition that V is equals to HQ, and it is associated with H into Q, where Q is the displacement vector associated with element 2, meaning that it is V2 theta 2, V3 theta 3. So H1 V1 LE by 2 H2 theta 2 plus H3 V3 plus LE by 2 H4 theta 3. So it is to be understood here that we are not concentrating on node number 1, as UDL is acting between node 2 and 3, node 2 and node 3. Therefore, the displacement vector here it is considered for element number 2, not for element 1. And the displacements are V2 theta 2, V3 theta 3. So this is to be considered first, where V2 and V3 are equals to 0. So after elimination, we have Le by 2 H2 theta 2 plus Le by 2 H4 theta 3. We have the equation for H2 and H4, and also we have calculated theta 2 and theta 3, and we have to substitute here zeta as 0 because we want to find the maximum deflection at the center of the beam carrying UDL. And when you do this, you will get the maximum deflection at the center of the beam as minus 0.0893 into 10 power minus 3 meter. So this is the numerical. One more numerical here, wherein both the elements carrying the UDL. The first element is consisting of the UDL 12 kilonewton per meter, and the second element having the intensity of UDL as 24 kilonewton per meter. So you can solve this problem without any worries. So only thing here you have to see the load vector. So load vector associated with the first element, which is F1, F2, F3, F4, is minus 24, minus 16, minus 24, 16. And when you calculate it for the second element, it is F3, F4, F5, F6. So F3, F4, F5, F6. And the first element is associated with F1, F2, F3, F4, and the second matrix is associated with F3, F4, F5, F6. And when you assemble these two, it is global load vector will be associated with F1, F2, F3, F4, F5, F6, corresponding to the degrees of freedom V1, theta 1, V2, theta 2, V3, theta 3. So it is required to add the corresponding entities, that is V1 we have to write as it is, that is minus 24, theta 1 it is minus 16, and V2 it is there at two places, minus 48 and minus 24, which is minus 72, and theta 2 is also there at two places, that is 16 and minus 32. So here 16 minus of 32 will be minus 16, and remaining minus 48 and plus 32 is written as it is. And we have to formulate the overall equilibrium equation. We have to eliminate the corresponding rows and column by applying the boundary condition. We can also find the maximum reflection similar to the previous problem. So lastly, I want to discuss this type of load. So it is a fixed beam wherein node 1 and node 3 are completely fixed, and node 2 is subjected to a point load of intensity 10 kilonewton, and also it is associated with rotation or movement of 20 kilonewton per meter at node number 2. So the force acting at node number 1. So here the finding of stiffness matrix for element 1 and element 2, it remains the same, and finding the global displacement vector, that is V1 theta 1, V2 theta 2, V3 theta 3, it remains same. And the only thing is here how to find the force vector. The force vector, here you have to write the force vector. Globally there are six forces which are acting, meaning that along each degrees of freedom there is a force. So there is F1 along V1 direction, theta 1 along F2 along theta 1 direction, F3 along V2 direction, and F4 along theta 2 direction, F5 along V3 direction, and F6 along theta 3 direction. So looking at this figure, definitely F1, F2 and F5, F6 are equals to 0. So only F3 is 10 kilonewton, and it is acting in the downward direction. So F3 is equals to minus 10 kilonewton. And when you see the moment here, so the moment is acting in anti-clockwise direction. The moment is acting in anti-clockwise direction. So for anti-clockwise, here it is considered as a negative, which is minus 20 kilonewton meter. So I will repeat it once again. So the difference for this particular problem with the previous one is it remains the same. Definitely in finding the stiffness matrices and assembly of the stiffness matrix and writing the global displacement vector and all, it remains the same. The only thing here, how to find the force vector. So force vector for element 1 and element 2 separately, if you find and add, it will be a wrong. it will be incorrect. And if you do it globally, that is globally, when you see the problem, there are 6 degrees of freedom system, and it is assumed that there are 6 forces which are acting along each degrees of freedom system. So F1, F2 will be equals to 0 corresponding to node 1, and F5, F6 will be equals to 0 for node number 3, and F3 and F4 associated with node number 2, we have the value as minus 10 kilonewton F3 and F4 as minus 20 kilonewton meter. And once you do this, and if you apply the boundary conditions, you will be in a position to solve this particular problem without any difficulty. So thank you for watching this video, and be share your opinion in WhatsApp. Thank you.